Thank you, Sebastian, for joining us today. We're ready whenever you're ready.
Great. Thank you for the introduction. Yes. So I will speak about what's going on in model checking in algorithmic meta-theorems, as you have said, how we try to push to dense graphs. Also, you will see a glimpse of different logics that are more powerful than first-order logic. So let me start by motivating algorithmic meta-theorems. So what we try to do is to find theorems that explain tractability not only for individual problems, but for whole classes of problems. So assume you have a big list of results, all of a similar flavor. Maybe you can group these results and find some common technique or something that these results have in common and group them to an algorithmic meta-theorem. This is something very nice. So the algorithmic meta-theorems that I want to speak about today are meta-theorems that we can obtain by describing those classes of problems by logic, because logic just provides a very elegant way to define problems. Yeah, it's a machine-independent way of defining those classes of problems. Two very famous examples are the logic, first-order logic, which can express many interesting problems. I assume you know first-order logic quite well. It's like one of the standard logics studied in model theory. You have existential quantifiers, universal quantifiers, and the Boolean connectives. So for example, you can express the dominating set problem of graphs. You would be stating here the existence of k elements, so that for every element, for every other element, either it's one of those k, or it is connected by an edge, hence dominated, right? And this is a very convenient way of stating this algorithmic problem, this algorithmic dominating set problem in a very generic framework in first-order logic. First-order logic can express many more problems that are interesting. The more powerful logic that we commonly study is monadic second-order logic, which additionally has quantifiers for sets, which makes the logic a lot more expressive, in fact. So here you see that we additionally have set quantifiers, those capital letter variables, and we can express, for example, the three-colorability problem by stating the existence of three sets. These are exactly the colors of the vertices. So every vertex must get one of the colors. It is contained in one of the sets. And then whenever two vertices are connected by an edge, this implies that they cannot get the same color. Yeah, this is exactly expressed by this formula here. And MSO can express a lot, many other problems like Hamilton path, and so on and so on. Okay, so what we like to do here is to have algorithmic meta-theorems optimally of this form here, every problem definable in a certain logic is tractable. And by this, we explain, of course, the tractability of this whole class of problems definable in the logic. And by tractability, we can mean anything that you like to have. Yeah, polynomial time solvability, fixed parameter tractability, approximability up to some factor. And this would be a great result because it provides then a uniform explanation why those many problems are tractable. Also hand in hand with those algorithms often comes a general algorithmic technique that explains how to approach the problems. And then finally, when we have matching intractability results, matching hardness results, then we know where the boundaries of those techniques lie, yeah, which is also very interesting, a side effect of those meta-theorems, I would say. So we can trivially test the truth of a first-order formula by just for every quantifier going over every possible vertex, how to instantiate the quantifier. Yeah, and this leads to a recursive algorithm, or you can see it as a game. And this trivially leads to an algorithm running in time size of g to the power of the number of quantifiers, yeah, size of the formula. This is trivial. Unfortunately, we cannot improve this actually under reasonable assumptions from complexity theory. So if we assume the exponential time hypothesis, then we cannot test if the graph has, for example, a dominating set in this time n to the little o of k, and we needed k quantifiers here, so g to the little o of phi is not possible under standard assumptions. Yeah, and for MSO, it's even worse, because we know that already for this fixed formula, 3-colorability, the problem is NP complete. So we cannot expect an algorithm running in time n to the f of phi for any fixed function f, right? Because this would give us for 3-colorability a fixed number and hence a fixed polynomial running time, and we cannot assume to get this. So this way that I stated the algorithmic meta-theorems as we like to have it, we cannot actually expect to have it because everything is intractable. So we have to relax this condition and restrict our inputs. Yeah, and this is the new goal now, to explain tractability not on all structures, but to have a classification of the structures where efficient model checking is possible. And hopefully then this may be sufficient also in our applications. Yeah, so lots of this now is about classification and establishing the boundaries of tractability for those model checking problems. So the starting point of meta-theorems was the super famous theorem of Courcelle, which he proved in 1990, showing that we can efficiently test MSO properties on classes of bounded tree widths. And we will see in a moment that this is actually something special and has a deep connection to the logic. It's not a coincidence that this works on bounded tree width graphs. And for first order logic, Piotr, you mentioned this already. So there was a long history of results of first order model checking. And then we showed how to solve it on nowhere dense classes in almost linear time. Yeah. So in the language of parameterized complexity, this linear time and almost linear time means that we can get rid of the exponent or the exponential dependency on the formula and have it isolated in a term depending only on the formula, this f of phi and epsilon here. This is a horrible function, but the dependency on the running time of the graph, this is almost linear. Okay, so why is it something special? Why does it have a deep connection to logic, actually? Why can we do FO model checking exactly here and MSO model checking on bounded tree width graphs? If we consider a class of graphs that is closed under taking subgraphs, so if you have a graph in your class, and then you will have also every subgraph, yeah, obtained by deleting vertices and edges, this will be also in your class, then we have the following deep connection between tree widths and MSO. Yeah, a subgraph closed class has bounded tree widths if and only if no MSO formula can define all graphs from the class. Yeah, so what do I mean by defining? I mean that we can put some additional colors on the vertices, and then we have a formula with 2 free variables, and this defines a new edge relation. So I will draw a new edge between 2 vertices x and y, if and only if this formula is true. Yeah, this is also known as a transduction. So this coloring step is something different from interpretations that you may know from classical model theory. We have those simple interpretations with just 2 free variables giving the new edge relation, and we have those additional colors. Yeah. So bounded tree widths, if and only if MSO cannot define everything. So we can expect hardness if we go beyond bounded tree widths, right? If we have unbounded tree widths, we can encode everything. So model checking will be as hard as on all graphs, right? So this is a very nice way of explaining the hardness, actually, or explaining exactly the limit of this method that Courcelle used to do model checking. It's dynamic programming over the tree decomposition. And this finds its limits exactly at bounded tree width graphs. Yeah, so we get from this connection here, hardness of model checking for classes of unbounded tree widths. We need a further weak assumption on the efficiency of encoding. Let me very briefly comment on this. Assume you have a class of unbounded tree widths, but you subdivide every edge 2 to the n many times. Yeah, and by this blowing up your input in a stupid way, in a sense, you will buy time simply by the stupid encoding. right? And if we assume that such things don't happen, then we have exactly the limit of tractability here for bounded tree width graphs. Okay, and exactly the same connection holds. We have this same deep connection between logic and graph classes for first order logic and nowhere dense classes. So again, for a subgraph closed class, the class is nowhere dense if and only if no FO formula can define all graphs from the class. Yeah, and again, we get the hardness of model checking. We cannot push beyond nowhere dense classes. Okay, so in the figure, we have those two logics, MSO a lot more expressive, but a lot less graph classes where we can do model checking. And for first order logic, we can push all the way to nowhere dense graph classes. Okay, this is quite nice. And it leads to a research agenda, of course, to find the most general graph classes now that admit tractable model checking. Yeah, for subgraph closed classes, this is essentially complete, but we want to get rid of the subgraph closure, right? And for MSO, and in fact for counting MSO, which is even more powerful, we have modulo counting in the logic. We can extend those model checking results to classes of bounded clique widths. This was shown by Purcell, Markowski, and Rotix. In their result, they were still assuming that a clique expression is given with the input, but we know how to approximate those clique expressions. There is a very recent result now showing how to do it in quadratic time. So combining these two results gives us full tractability of model checking for CMSO on classes of bounded clique widths. And again, we have this super nice connection, clique widths and logic. A class has bounded clique widths now without any assumptions on subgraph closure or so, if and only if no CMSO formula can define all graphs from C. Yeah, and again, we get the hardness of model checking exactly from this. So this is a really nice connection between those tractability results and the corresponding hardness results, a logical meaning or some deep connection between graph theory and logic here. So in the figure, we get the dense analogs on the right. Yeah, bounded clique widths is a dense analog of bounded tree widths where we can do MSO and even CMSO model checking. And this classification is essentially complete. There is one big open question left here on this slide, which is the question if we can replace in this characterization CMSO by plain MSO. Yeah, so does a class C have bounded clique widths if and only if no MSO formula can define all graphs from C? At this point, we need the counting power to encode everything. And whether plain MSO suffices, this is strongly related to a famous conjecture of Sese, whether you can find all graphs, essentially all grids, as soon as you have unbounded clique widths. Okay. So we want similarly to push the first order limits of tractability from nowhere dense classes. Yeah, we got for subgraph closed classes, those limitations were the nowhere dense classes. So the classification here is also complete for subgraph closed classes. And we want to push, of course, to the dense world, right? So let me take now a class of graphs that is closed under taking induced subgraphs. And let me conjecture something, or let me ask, what would be your conjecture up to which point can we push when you look at the way how I built this talk, how I led to those slides? What would be your conjecture? Up to what point can we go?
I'm too afraid to say something stupid.
So just look at this characterization here. How do we get the hardness for not nowhere dense classes? Don't give me a name, give me a property, a connection to logic.
That can define everything somehow?
Exactly. We want to push exactly to those classes where first order logic cannot define everything. and just drop this assumption on the subgraph closure and take the classes closed under induced subgraphs. Exactly, thank you. So we conjecture that model checking for first order logic should also be tractable on every class C, where no FO formula can define all graphs from C. Yeah, just how we got the intractability for all the other graph classes that we looked at. Okay, and this, of course, has a name now, as you would expect, because this is a super important notion in classical model theory. Yeah, when can you not define everything with first order logic from some graph class? This must have been studied in first order model theory with classical interpretations, in fact, but also in this transduction world. And this is something I give you just the name now, which is called monadically dependent, or NIP. Yeah, and this is some very important notion in model theory. It showed up in this whole classification program of Shelah, who classified the first order theories as being well-behaved or very complicated. Yeah, if you can express everything, can define everything, then it's a complicated theory. If not, it's rather well-behaved. And these classes where we can add the colors to encode everything, these are called monadically dependent classes, monadic NIP classes. Okay, so in the figure, we have that from nowhere dense classes, you cannot define everything. From classes with bounded clique widths, you cannot define everything, even with MSO. So both of these notions are unified with the notion of monadic NIP. And we try to push towards model checking for monadic NIP classes, because we know that this should be some natural limit of doing efficient model checking. Okay. So how can we expect, or what would be the methods to push actually? And there is one quite natural way. When we look at the way how we actually got to bounded clique widths. So I defined bounded clique widths as we cannot define everything with MSO from bounded clique widths, but there is a different view. It is, I can define every class of bounded clique widths actually in the class of all trees, or in the class of bounded tree widths with an MSO transduction. Yeah. So from the structural point of view, or the logical point of view, bounded clique widths is nothing than being structurally a tree. Yeah. And being a tree means I can define it from a tree. Yeah. Do this definition, this transduction. Right. And I want to apply this same concept now for first order logic. I want to take the classes that I understand very well, those nowhere dense graph classes in particular, and I want to apply a first order transduction on top of this, and then get something that structurally looks exactly like a nowhere dense class. And I somehow want to apply my methods that I know for nowhere dense classes in the dense world, yeah, in this transduced graph class. Okay, so what do we have here? Let me take any graph property that I like, and then say that a class D has structurally this property. If I have a pre-image, a class C, with the property I'm looking for, and then I can obtain the class D by a first order transduction. Yeah, so I have something with the property, I apply a first order transduction, and then it should somehow structurally still have the property. Yeah, and this is now a class with structurally P. So when the classification on the sparse world was complete, people quickly turned to ways to look at dense classes. And this was the first result here. People looked at classes with structurally bounded degree. This is work by Gajarski et al. In 2016, who showed that FO model checking is tractable on classes with structurally bounded degree. Yeah, so the very, very basic class, bounded degree, apply a first order transduction. They could provide a full characterization of the structure of those classes and recover actually the sparse graph class and apply the model checking procedure then on this base class, which is a very nice approach, and which opened the door to look at the other classes in exactly this way. Yeah. So in 2018, 2 years later, we could push these results to classes with structurally bounded expansion. And then in this year, we were actually able to push to classes which are structurally nowhere dense and in fact, locally structurally nowhere dense. This is a very new result. And I will show you in a second how we approach this problem and which methods we can actually push from nowhere dense classes to structurally nowhere dense classes. Okay, so there is now a third line here, the structurally line, the transductions of our sparse classes. We have classes with structurally bounded tree widths, yeah, applying only a first order transduction on a bounded tree width class. Then with an MSO transduction, we go to bounded clique widths. And then we have this whole line here parallel to the sparse world, leading all the way to structurally nowhere dense classes and locally structurally nowhere dense classes, which are again also all monadically nip. So it's a step towards a conjecture, but we are still far away from this. Okay, so let me give you an idea how to approach this model checking problem. So it is all built essentially on Geifmann's locality theorem, which states that every first order formula can express only local properties, right? If you want to express that two elements of a structure are at a certain distance to each other, you need to invest quantifiers for this. Unlike for MSO, where you can just guess the vertices on the path, right? And Geifmann captures this quite precisely. Depending on how many quantifiers you have at hand, you can express only things up to a certain locality radius. Yeah. So every first order formula with 3 variables is equivalent to a Boolean combination of formulas that are local around those 3 variables. Yeah. So you have to look only at some R neighborhood in your graph to tell the truth of your formula, and 2 sentences of such generalized independent set formulas. Yeah, what does this formula state here? It states the existence of S elements that again locally satisfy a certain property and then have pairwise a great distance. Yeah, so again, some local things you can say, they can be distributed somewhere in the graph, they need to have a large radius. And furthermore, you can efficiently transform your formula into such a Geifmann normal formula. Okay, so this theorem gives a very clear path on how to approach the model checking problem. All you have to do is understand the local neighborhoods, right? If you can do model checking locally, then do it and plug together your statements, what you found out about the elements themselves, and plug it together by Geifmann's theorem. Yeah, so we have to understand the local neighborhoods, and here is how we did this for nowhere dense graph classes. We invented a game to explain how the local neighborhoods look like. Yeah, the so-called splitter game. Assume we want to understand R neighborhoods, so we play for some radius R. 2 players are playing. Called connector and splitter. The connector wants to show that the graph is complicated, that the neighborhoods are complicated, and the splitter wants to show that they are actually simple. Yeah, so what will connector do? The game proceeds in rounds. In each round, the connector chooses a vertex, and we look, or we restrict the future game to the R neighborhood of this vertex. Yeah, so connector says this neighborhood is actually super complicated. And then splitter, she will say, well, it is still complicated, but let me delete 1 vertex. Yeah. And then we iterate this procedure with the vertex deleted. We have a new arena, the R neighborhood minus this vertex, and then connector again points to a neighborhood that is now complicated, splitter deletes, and so on. So after at latest n many rounds, the graph will be empty. Right? So I have a figure for this again to understand this game. This is our whole graph. Connector points to this complicated neighborhood. Splitter deletes a vertex. We localize again. Connector chooses again this radius R ball. Distances have changed now by our restriction and the deletion of the vertex. So the arena gets smaller and smaller. And after at latest n many rounds, the game has terminated. And when do we gain something? If we can prove that the game terminates earlier than this, earlier than this trivial bound that we have. And what we could prove is that the class of graphs is actually nowhere dense if and only if for every radius, splitter can win in a number of rounds depending only on the radius, completely independent of the graph size. So what do we get from this? We can simply use this Geifman normal form, look at our radius, bounded radius balls, and recursively decompose them, do our model checking recursively in the very latest round when only one vertex is left. This is trivial, and then we go up this game tree and do model checking. So there is one caveat. If you try to do this recursively and you recurse into all the neighborhoods, it could be that they are strongly overlapping and that actually in all neighborhoods you see all vertices again and again. So you have a recursive procedure, a recursion tree with a bounded depth. However, the branching degree could be n, the size of the graph. And this naive implementation would lead possibly to a running time of n to the L, where L is the number of rounds that we have here. And then we don't really gain anything, right? Because this number L is usually a lot larger than the quantifier rank of the formula. So our trivial algorithm doing it in n to the quantifier rank is much better, right? And we solved this issue by grouping overlapping neighborhoods into so-called clusters and getting a sparse neighborhood cover so that the branching degree of this recursive procedure of this recursion tree was bounded by n to the epsilon. And by this, we could efficiently solve the problem. Okay, so this is a game now characterizing exactly the sparse graphs, the nowhere dense graph classes. And the question is, how do we extend this to the dense world? And well, we invented a new game, which is called the flipper game, which is super similar in spirit to the splitter game, and the strategy to approach model checking will be very similar. So in the flipper game, we look at flips between vertex sets. So if we have two sets A and B, a flip between them simply inverts the adjacency between vertices of the two sets. So if there was an edge between two elements of A and B, then there is no longer an edge. If there was no edge, then we insert one, complementing this adjacency relation. In the splitter game, connector was choosing those local balls. Splitter chose a vertex and deletes it. And the flipper game is exactly like this, but we have a flipper instead of a splitter. So connector again chooses those complicated balls. And flipper picks two arbitrary sets and flips the adjacency between them. And then we iterate this in exactly the same way. So again, we have our graph, we have the local neighborhood, and now flipper will pick two sets and invert the neighborhoods here. And then we go to the new R ball and we iterate exactly like we did before. Okay, so interesting game. What does it characterize? We could very recently characterize those graph classes where the flipper game is one. And it turns out that there is a new notion now from classical model theory showing up. We could prove that a class of graphs is monadically stable if and only if, for every radius R, the flipper has a winning strategy to win in a bounded number of steps, winning, depending only on the radius R. Furthermore, we can efficiently compute this strategy, which is super important, of course, for our model checking algorithm. And with, so what is this strange new notion, monadic stability now? It turns out that stability is one of the key notions in classical model theory. We had already the notion of dependence, and stability is one other very important notion. Actually, it's the more important notion in this classification program of Shelah. And the monadic stability comes again into play by this coloring of the vertices. And there was also a very interesting and surprising result also just recently proved that for hereditary classes, so classes that are closed under taking induced subgraphs, the notion of stability, as we know it from model theory, coincides exactly with monadic stability. Yeah, so we have a collapse when we consider those hereditary graph classes. So this seems to be something super important, supernatural, when we look at graph theory and when we look at the closure properties that we usually have there, the hereditary graph classes. Yeah. So very surprising, very nice connection. This is great. So what are we lacking? We are lacking the sparse neighborhood covers to do model checking on monadically stable graph classes. Yeah. What we could prove in our result.
So you say that this strategy you can compute efficiently.
Yes.
I'm just wondering, what is the input to, like, you get a class of graphs, yeah? So what do you know about this class before you start computation?
So you get as input the just the graph and the radius.
Yes.
And then we will play the class, and your strategy will be obtained, or actually the bounds for the strategy will be obtained from the class. But your strategy will be, in a sense, uniform, in fact. And it will be efficiently computable just from your input graph. Yeah, so there is a way that you can play with every graph, actually. And the number of rounds will depend on your class. Yeah. If you are familiar with the original strategy on nowhere dense graph classes, there was this notion of uniform quasi-wideness, where you were ripping the graph apart in consecutive rounds, yeah, in a uniform way. And a similar thing is happening here on monadically stable classes. So you will be able to do flips, and the more vertices are picked, or the more neighborhoods are picked, you will be ripping apart your vertices by flips instead of by vertex deletions. Yeah? And what you need to know is, well, the strategy will evolve as the vertices are picked by a way of defining those flips that bring vertices far apart from each other. Yeah, so you need no additional information about the class or something. This will only determine the number of rounds you need. Your strategy is computable just from the graph and the radius you get.
Okay.
Mm-hmm.
Nice.
Exactly. Okay, so what we are lacking to do model checking, on a high level, the model checking approach works exactly as we did for nowhere dense classes. It's more complicated, but the underlying idea is the same, but we don't have the neighborhood covers for monadically stable classes. Yeah. What we could prove now is that those neighborhood covers exist for structurally nowhere dense classes, and there we get the tractable model checking. So in the figure, we can do model checking here up to locally structurally nowhere dense classes. The monadically stable classes sit on top of this. And what we need to show is that we have sparse neighborhood covers for these graph classes, for monadically stable classes. And we conjecture that they will, in fact, exist for monadically nib classes. Okay. Let me present you those neighborhood covers such that you can take a homework from this talk. And please send me the solutions. So what are those sparse neighborhood covers? So we want weak neighborhood covers, sparse weak neighborhood covers. What we want to do is we want to cover the R neighborhoods of vertices. Yeah, so we want to have clusters that group nearby neighborhoods into those clusters. So the first condition that we have is that every R neighborhood is contained fully in some cluster. Yeah, so for every vertex, there exists some cluster so that the R neighborhood is contained in the cluster. Then, of course, there is a trivial solution. You can just take the whole graph to cover everything, right? But then the radius may be unboundedly large, and we want to apply those locality methods, right? So what we want is that every cluster is a subset of an S neighborhood for some vertex in the graph. Yeah, we don't need that the cluster as an induced subgraph has bounded radius, but it must be contained in some local neighborhood. Yeah, so that we can play the flipper game for those surrounding balls and get the structure simpler and simpler. Now there is a second trivial solution. If we just want bounded radius, we could just take all the R neighborhoods, right? But then we would have a large overlap of those clusters, and we would have this this branching, this recursion tree could have branching degree n again. So we want a small overlap, small degree, and what we want here is that every vertex appears only in a bounded number of clusters. And what we allow in those sparse weak neighborhood covers, so that we can use them for model checking, is that there is a function S for those for the radii that depends only on R, and then we can have some non-constant dependency on the graph size, but this shall be only n to the epsilon essentially. So there shall be a second function g of R and epsilon, so that this degree, this overlap of the clusters at any point, this must be bounded by g of R and epsilon to the g times g to the epsilon for any epsilon greater than 0. Yeah, so this is the one missing piece. You don't even have to show an algorithm to compute them. Only the existence is sufficient. As we could show, if neighborhood covers exist, then we can actually approximate them quite well and sufficient for our needs. So really the model checking depends only on this, the existence of those sparse neighborhood covers for monadically stable classes. Okay, let me mention one last graph class, which will complete essentially what we know until now, the advances on algorithmic meta-theorems for first-order logic. Also very recently, the new notion of twin widths popped up, and it again has a super strong connection to first-order logic if we look at ordered graphs. So a class, again, is a class that is closed undertaking induced subgraphs of ordered graphs has bounded twin widths if and only if no FO formula can define all graphs from the class. Yeah, so somehow there is this super strong connection between logic and the classes where we can work with a nice structure theory here. If we have an unordered class, then we can do model checking on classes of bounded twin widths if a so-called contraction sequence is given with the input. This was shown by Bonnet et al. In 2020, where they also introduced this notion of twin widths. But this is only a conditional result. We have no idea until now how to compute those contraction sequences. But if the class is ordered and still has bounded twin widths, then it is known how to compute it. Then model checking is tractable, and we have this if and only if condition. Yeah, so the exact boundary for tractable model checking. This was shown by Bonnet et al. In 21. Yeah, so again, a very nice connection, and this is what we know until today here, classes of bounded twin widths, generalizing classes that structurally exclude a minor and classes with bounded clique widths. And also they are monadically nib. Okay. Are there questions up to this point? Because this is the picture for first order model checking, and I want to change the topic now a little bit. This doesn't seem to be the case, so let me continue.
Just to be sure, the result for bounded twin width, you need to know the ordering of the when you
yes.
That represents the twin width, yeah, and then there is nothing conditional about it with respect to clique width, yeah. There we can.
So for clique widths, we don't need to know anything. Exactly. For twin widths, we need to compute this order.
What was the reason for clique width that we don't need it? Like.
So for clique widths, we can compute a clique expression, or we can approximate the rank width actually, and the rank width is functionally related to the clique width, and then we will work with the rank decomposition, the branch decomposition for rank width, and can do it even for MSO. Exactly. And if we have an ordered class of graphs with bounded twin widths, then Bonnet et al. Showed how to actually compute a good contraction sequence and have the full FPT model checking. Exactly, which is a great result again, and a great connection to logic. It's amazing that this notion wasn't found earlier, and it's really cool. Okay, so I will change the topic a little bit now. I want to ask the question, we know now that first order logic can express only local properties. So is it actually the right logic if we want to do meta-theorems? Yeah, can we express what we really like? Because connectivity is such a simple algorithmic question, right? We can just do a graph search and answer the question whether two vertices are connected. So this locality is formalized by Geifmann's theorem. You have seen it. There are more ways by Hanf's theorem and so on. And we cannot express those simple connectivity properties like connectivity if the graph contains a cycle, other interesting properties from parameterized complexity, like can we delete k vertices so that we have no cycle left? This is the feedback vertex set problem. If the graph is bipartite, if the graph is planar, the disjoint path problem. Yeah, all of these problems, we know efficient algorithms. So at least the problems are fixed parameter tractable. And first order logic cannot express it all. Yeah, which is a pity. So all of these properties can be expressed in MSO, but we know that this comes at a price, right? There are other logics that are commonly studied, especially in database theory, like least fixed point logic, transitive closure logics. But the model checking problems for all of these logics are quite hard. Yeah. So essentially, as soon as you have unbounded tree widths, exactly as for MSO, you get hardness results. Yeah. So all of these logics are hard on planar graphs of maximum degree 3. So this opens a new research agenda. We want to have logics that can express these properties, but where the model checking problem is still tractable, right? And what we try to do here is to take first order logic as a basis and then add further predicates or operators that can express exactly those properties that we are interested in. And at the same time, of course, we still want to keep our efficient model checking. Yeah, so let me give you an example of what's going on here. So the group in Montpellier and Bergen, they introduced compound logic. There you have first order logic, and then you have additional modulator sentences, yeah, such that you can express such things as the feedback vertex set problem, where you can delete a set of vertices satisfying a certain property, which is specified in MSO. And then you want to arrive at some target property definable in first order logic plus minor exclusion. Yeah. So this is a quite complicated logic, I must say. It looks a bit like a programming language, but there were some tractability results for these logics, and you get quite powerful meta-theorems from compound logic. The model checking problem is tractable on classes that exclude some minor. And then we introduced some much simpler logics really made for those connectivity queries. Yeah, and still I will show you that there are quite interesting connections. So separator logic, here you can query connectivity after vertex deletion. This logic was independently also introduced by Miko Weibo-Janczyk in Warsaw. And we proved also with the Warsaw group with Michał Pilipczuk and Szymon Torunczyk that we can do model checking on classes with excluded topological minors. And super surprisingly, again, we have this characterization of graph classes in terms of definability in logic. Yeah. So if we have a subgraph closed class of graphs excluding some topological minor, or it excludes a topological minor, if and only if no formula of separator logic can define all graphs from C. Yeah. So exactly what we did, this classification for FO and the correspondence to nowhere dense, classification for MSO on subgraph closed classes corresponding to tree widths. We have something suddenly for those classes studied in structural graph theory, characterizing exactly the classes excluding topological minors, which was quite surprising and to me is just another very beautiful connection between logic and graph theory. We also looked at an extension of first order logic with disjoint paths. And we very recently showed that also here we have tractable model checking on classes with excluded topological minors. Okay. Let me show you this separator logic because it gives a very nice meta-theorem and a very nice methodology to do model checking, which is maybe new and very interesting. So in the figure, we have those, this staircase here now, gradually going between first order logic and MSO.
Ik konnte Kees hier nou niet in deiner Apple Music.
I awoke Siri. Sorry for that. Okay. So what is separator logic? We have classical first order logic, and then we have a predicate con, which states that two vertices x and y are connected when we delete the vertices z1 to zk. Yeah, so we don't only want to query are x and y connected, but we also want to delete some vertices. Yeah. What can we express with this? Of course, we can ask if the graph is connected, right? We simply ask for all x, for all y, con 0 of x and y. Yeah. We cannot query with con 0, however, if the graph is acyclic. Yeah. Because if we have a connected graph, the connectivity predicate gives us nothing, right? Every vertex will be connected. This is like a clique. The clique can be inverted. There is no information. Yeah, this is why we wanted to have this additional power of deleting some elements, right? So we can ask more complicated queries with those vertex deletions. For example, is the graph K connected? Yeah, it is if for all K minus 1 vertices that you delete, the remaining graphs remains connected. Yeah, this is exactly what the con K minus 1 predicate is made for here. We can query if the graph contains a cycle. Yeah, what do we have to say? We have 3 vertices that are connected in a path. So we have x, y, and z. And then if we delete y in the middle, then there shall still be a path going in another way. Yeah, so x and y, z are still connected after the deletion of y. Then we can ask about the feedback vertex set by quantifying the k vertices that we delete, and then the graph shall be acyclic. Yeah, so we can express those interesting properties that we are interested in. And also very interestingly, we were pointed to the data structure community where they consider the following problem, which is called the connectivity under batched vertex failures in the dynamic subgraph model. What you have here, you are given some graph, you are allowed to do some pre-computation, so construct a data structure, and after that, you want to be able to answer such connectivity properties after vertex failure in a very quick time. Yeah, so you want to set some failed vertices, V1 to Vk, they shall no longer be usable, and then you want to query are S and T still connected without those failed vertices. Yeah, this is exactly our base atom that we added to first order logic that those people in the data structure community want to answer, right? And yeah, they are investing a lot of time to come up with good data structures, to have quick update and query times here. And what we have here as results, so there are naive approaches, of course. If you pre-compute nothing and just re-answer your query, then you have a very expensive query time and no update time. Otherwise, you can pre-compute for all pairs of vertices, are they connected or not, right? You do your query in constant time because you just have a table. If there comes an update, you just recompute all the, for all the pairs, are they still connected, right? So this is the naive way. And now there is a a balance between how much time you can invest. Yeah, and what Duan and Petty did with a complicated data structure here is an O of k query time, and then there was a polylogarithmic dependence on the graph size. Also, very recently, there was a randomized algorithm that for the first time achieved some independence on the graph size for your update times. And what follows from our results is the first fully deterministic such data structure. Yeah, so for every fixed k, you have a constant query and update time. In fact, we have no update time at all because we can answer our atomic predicate simply in time depending only on k. Yeah. And let me give you the ideas of how to do this model checking. So assume for a second that your graph is k+1 connected, right? Then the deletion of any k vertices will not disconnect your graph. So your connectivity predicate is useless and you can do plain FO model checking. Yeah. So on very highly connected graphs, the problem is very easy. Yeah. And we want to relax those conditions on the connectivity of the graph and work with unbreakable graphs. And let me give you the definition of this. So a separation in a graph is a pair AB of vertex subsets, so that the union of A and B is the whole vertex set, and such that there is no edge from one side to the other that does not have one end in the separator, which is the intersection of the two sets in the separation. Yeah, so as you know it from tree decompositions, you have those separations in the intersections of the bags. And now we call a graph QK unbreakable if for all separations of small order, you cannot break the graph in balanced parts. Yeah, so for each separation, one of the parts must be small, of size at most q. Yeah, and what you will have, if you look at any set S, then you cannot break the graph in a balanced part if it's QK unbreakable. That is, every component of G minus S is either very small or super large. Yeah? And what I claim now is that we can use this combinatorial information to show that on unbreakable graphs, the connectivity predicate can be evaluated in constant time. And in fact, the full separator logic, FO con K, collapses to plain FO. Yeah, and then we can do our plain FO model checking. And this is just nice. So how does it work? Let's assume we are in our unbreakable graph, and let us look at the vertices S and T. We want to know, are they connected after the deletion of V1 to Vk? So what we do, we just do a depth first search in the graph where V1 to Vk have been deleted, starting at the vertex S. We don't complete the search, but we stop it when we have visited Q+1 vertices. Yeah? Either in those few steps we found the vertex T, then we can of course return T is reachable. Yeah? If we did not find it and we explored the whole component, then we know that we are in the small component, yeah, or in one small component, and we can give a negative answer. If we did not explore the whole component, then we know that we are in the unique large component. Yeah. Now we restart our search from T, again stopping when Q vertices have been visited. Yeah. Either we explored the whole component and didn't find S, yeah, we return the negative answer, or also here we get that T is in the big component, and then we get for free, without searching the whole graph, that S and T are connected. Yeah, so constant time, where Q is considered a constant, to answer this global query. Yeah, this is super nice, very nice combinatorics here for this collapse. Okay, how can we proceed? Of course, not every graph is unbreakable, QK unbreakable, but there is a super nice decomposition theorem by Zygan et al., who show that actually every graph can be tree decomposed in a nice way, so in a tree-like way, so that every bag is QK unbreakable in the graph below, such that the adhesions are small, so the intersections between two bags are small, and we can efficiently compute this. Yeah? And what we can do now is just a dynamic programming from the leaves to the root of the tree, combining our information using that first order logic always collapses on those individual bags. Yeah, this is super nice. For disjoint path logic, we showed something similar, so even stronger. If you have an unbreakable bag and you don't exclude a minor, then actually the disjoint path predicate will collapse to plain FO. Yeah, which is just nice. You can use all your tools for first order model checking on those unbreakable bags. So we do assume here that the class excludes a topological minor. This is to have the dynamic programming over the tree working, because we need to encode some information on the types, on the children, on those decompositions. Yeah, but the method is just super nice, and maybe you can take this away as one of the methods. This decomposition into the unbreakable parts, and that some global combinatorics actually collapse to local combinatorics exactly as we need it for first order logic, and then we can combine those informations. Okay, and then let me conclude with this last slide, the map of the universe as we know it at this point. So we have first order logic and the boundaries of tractability at this point at locally structurally nowhere-dense classes and bounded twin-width classes. The big conjecture that FO model checking could be possible on monadically nipped classes. For monadically stable classes, we will be able to do it if you do your homework, finding those sparse neighborhood covers. Exactly. For MSO, we have the full classification. And now we have this interesting new question: can we characterize commonly studied graph classes by logics, exactly as we did now with first order logic, separator logic, and MSO, by a graph class has a certain property if and only if a certain logic cannot define everything from this class. Yeah, which is a just beautiful connection between logic and graph theory. So with this, thank you very much for your attention, and please ask me any questions.